Hello everyone. In our previous videos we have seen the introduction, instrumentation and the principle of the capillary electrophoresis, how the electro-osmotic flow works and how it carries the analyte components towards the cathode and how they get detected and get separated. In this video we'll see how the electro-osmotic flow is being controlled by various parameters. We are calling it as variables. I am taking 6 important variables. The first one, let us start. It is the buffer pH. The effect is osmotic flow. I am abbreviating, simply I am calling electro-osmotic flow as osmotic flow. The osmotic flow increases as the pH also increases, and this effect is more pronounced in the silica capillaries, which we have seen in our last video. So this becomes a very convenient method to control the osmotic flow. Suppose if I want better separation, I can increase the osmotic flow by simply increasing the buffer pH. But we must also remember that there should be a balance between the osmotic flow and the effects of the charge on the analyte components. The second important one being the electric field. Osmotic flow, it changes proportionally with the electric field. So osmotic flow increases as the electric field also increases. But whenever the electric field is very high, more amount of heat is generated in the capillary. This may lead to production of the sparks, or it may also lead to short circuits. So this heating in the presence of electric field is called as Joule heating. Suppose if you try to lower the applied electric field, then it may affect the separation efficiency. So we have to maintain a balance in such a way that the electric field is not very high, so that it may lead to some short circuits, or it should not be very low so that the separation efficiency get affected. So even electric field need to be optimized. The third important variable is temperature. Osmotic flow decreases with an increase in temperature. So a change of about 2 to 3% per degree Celsius in the osmotic flow can be seen. And controlling temperature is one of the very easiest ways. Fourth one being the organic modifiers. So with the help of these modifiers, usually the osmotic flow is found to decrease. These modifiers, when added into the bulk solution, they will change the potential at the capillary wall. They also alter the dielectric constants of the running buffer and also the viscosity. So usually these modifiers, they will decrease the osmotic flow, and the changes within the osmotic flow are very complex, so these need to be properly supervised. Coming to the surfactant, when a surfactant is added, osmotic flow can increase or decrease, and these surfactants, they can change the magnitude of the osmotic flow. It can even change the direction of the osmotic flow. Usually the osmotic flow direction is towards the cathode. Supposing cathode is present to this end, osmotic flow will move towards the cathode. But in certain cases, due to the addition of these surfactants, the osmotic flow could be completely reversed. Usually it is found that whenever anionic surfactants are added, that will increase the osmotic flow, but whereas whenever the cationic ones are added, that is found to decrease the osmotic flow. These effects they generally occur due to adsorption through hydrophobic or ionic interactions. So it could be hydrophobic or it could be ionic interactions. In some cases it could be both hydrophobic as well as ionic interactions. The last one is the covalent wall coating. Again, this may increase or decrease the osmotic flow. Suppose if at all we have some neutral coatings, these neutral coatings will reduce the negative charges on the capillary wall, which will lead to the reduction of the electro-osmotic flow. Ionic coatings, they have considerable effects. Either the osmotic flow could increase or it could decrease depending on the type of the coating. So these are the variables that affect the electro-osmotic flow. And this is about capillary electrophoresis, one of the best separation techniques which is exponentially rising in the present era. Thank you.